Hello and welcome to week 9 in artificial intelligence. This week we're going to be talking about multi-agent decision making and learning from examples. So our agenda, will go over the assignments, then we'll talk about chapter 18, which deals with multi-agent decision making, and then chapter 19, which is around learning from examples. So jumping right into the assignment. So we're into between week 8 and 11, obviously. So you should start turning your attention towards the deep learning framework assignment, the paper that's coming up in week 11, and also potentially start thinking about your project for learning in week 12. This week, week 9, you're to talk about machine learning. So what is machine learning? Define it. Find a scholarly article with a description of an application of machine learning. And discuss the article and the outcomes associated with it. One of the things you'll find, I suspect, is that machine learning has lots of different meanings to lots of different people. I'll leave it to you to choose your definition. Make sure you do back it up with some citations or some rational explanation as to what it is. But do consider the fact that there are lots of different opinions. So think about that. Some useful resources for this course, the same as they've been through the other lectures that we've talked through. The Berkeley resource is very good. You should spend some time looking there. The GitHub repository has basically the code and pseudocode associated with the text in various languages. So moving into multi-agent decision making, which is chapter 18. So what are the properties of multi-agent environments? First of all, this is kind of an advanced topic. Keep that in mind. You can take a course in this at a graduate level. So, but it is relevant to real world scenarios because there are oftentimes environments where there are multiple agents potentially with competing goals interacting with each other. A perfect example is something like a stock market trading environment, automated trading, where you have agents who all have a competing agenda of making money for the respective overlords, if you will. And it's not something where they're going to be competitive. And there are other situations where they are potentially cooperative in nature. And in order to deal with this topic, you have to kind of have some understanding of lots of different topics and lots of different domains. So here's a basic idea of the elements that may go into a multi-agent system. So you may have things which we've talked about somewhat in the past, psychology, obviously artificial intelligence. There's also some sociology in the mix and maybe some economic theory, some decision theory. You probably need to implement it in something, so you're going to probably need to write it in a programming language. And you're also dealing with distributed systems, so you have mobility and communication going on. So lots of different stuff have to go together to deal with multi-agent decisions. So your first kind of criteria is, well, how many decision makers are there? If there's one decision maker, uh, then you may have like multiple agents with one that is tasked with making the decisions. Uh, in that scenario, you assume that they're a benevolent agent, that they do what they're told, right? That's basically the assumption of the benevolent agent assumption, is that the agents are going to do as they were instructed to do in this scenario. They must work together. That implies they have to synchronize their activity so that they aren't interfering with each other even when they're trying to cooperate. And they work together with the intent of reaching some decided goal along the way. So a set of actions to reach some goal. And you must have a decision maker who can handle multi-effector planning, and that's a fancy way of saying concurrent planning. That means that you may truly have agents doing things at exactly the same time. Another sort of world is, well, the other, right? Multiple people or multiple agents are making decisions. So you can think of this in a real world scenario. You might have a situation where it's a work environment that is very authoritarian. There is a boss, one boss, and a lot of workers, and the workers do what the boss tells them, right? That's one approach. A more emerging sort of leadership style is a team leadership style where the team decides as a whole what they do. There's generally coordination going on, but it's not necessarily a single person that's making the decision. And in fact, the whole team may be held accountable for the outcome. So in that scenario, there may be a certain amount of conflict going on in the decision making. So the next question is, what is there a common goal where they're working together to reach a common sort of thing, and that becomes a coordination problem. So everybody wants the same thing. It's a matter of how that happens, not if it should happen. If it's a personal goal, then you might have a zero-sum situation where I win at your expense. And in that situation, then we're definitely not going to be on the same plan, and you're not going to be doing what I tell you to do, right? And rightly so. So this is where we start getting into the concept of game theory and the use of strategic decision making. That'll impact various elements of this domain, but be it the agent design of how they might make their decisions and how they calculate their utility, the mechanism of how that environment is put together, of how it behaves, what are the rules of this world. It may be that there is a cooperative game where you have a binding agreement of some sort between agents to work together. You can think of that as sometimes you have partnerships in organizations where two potentially competing partners join together for some common good. Generally speaking, that's a short-term sort of relationship, and maybe one partner benefits more than the other. If you think way back to the beginning of the computing industry, IBM and Microsoft did that to create OS/2. And then Microsoft made Windows NT very shortly thereafter. So which one can you buy today? Well, Windows NT is the heart of most modern Windows operating systems, so give it a thought. Non-cooperative games is there's no agreement to work together. And the word game here isn't necessarily a recreational thing. I want to make sure that's understood. Games are a way of viewing interactions amongst agents and actors. So there's generally some mechanism of value, of score, of utility, and potentially competing constraints or considerations. So whenever you talk about multi-agent planning, kind of three sort of ways that can go as well. You can have interlocked execution, where basically there's the order of each agent's execution plan is preserved. They do things basically in the same order, but it doesn't handle true concurrency. So if you have a single, back in the operating system sort of world, if you had a single processor with a single core, you don't have to worry too much about true concurrency because everything takes its turn. It's that sort of concept. True concurrency uses basically a partially ordered plan. So you come up with something that's basically the order of execution, but each individual agents do their part in potentially different orders or different overall orders, but inside of their order, they're going to do it in a certain way. So they have their piece of the puzzle. They're going to do theirs in a certain order. The overall order of execution, though, may be different. And then you have this the last one is a synchronization sort of solution where there's essentially a global clock. So the agents ask what time it is periodically of this global clock, and it brings things into essentially lockstep execution. Moving on to, well, what if we're not all together for the same reason? So non-cooperative game theory. There's various strategies that may be utilized. You may have a pure strategy, which is a deterministic policy. You always do something based upon inputs. A mixed strategy, which does that. It kind of does somewhat of a pure thing, but it randomly does something else. And depending upon where you are on the continuum, you could be all the way over to a truly random agent, which may or may not be all that successful. But if you're interacting with another agent, their strategy, their policy of how well they're going to do a certain thing can be very challenging for you if you don't know what they're going to do, right? So you have to consider that as a consideration of if you're not cooperating and they may potentially be conflicting with what you're trying to do, you're probably going to be concerned with what they're likely to do next. And if you can't predict it because what they're doing has a randomness to it, that's kind of challenging. And a strategy strongly dominates, and that's the key word, if the approach always gives the best outcome. So if it always is the best solution, it strongly dominates the other approaches. The strategy weakly dominates is if it's at least a little better in at least one way, but it's no worse than any of the others in the other ways. So you will likely choose a dominant strategy, and a dominant strategy is one that you're going to be doing most of the time. And dominant strategy equilibrium is that there's no reason to do something different. So basically, all of the players may settle into a dominant strategy. because you doing the same one. And Nash equilibrium is kind of that same sort of concept, except there's no change that can be made in strategy to benefit anybody without detriment to someone else. So social welfare versus what's best for one player. You may have a situation where social welfare is the guiding principle. These agents may be well behaved and they may do what's best for the entire system, even if it potentially is at the benefit of one individual, or maybe one doesn't get as much as they might otherwise. The Pareto optimality is the best outcome for all players without improving one at the cost of another. So you basically reach some level where the only way that it gets any better is if somebody else pays. So you typically may not want to do that. And a utilitarian social welfare is a measure of the overall outcome for the entire situation or environment. And that could be very bad for one of the actors, but good for the overall environment. So those are the kind of the variations on the theme. When you talk about cooperative game theory, you have a group of players, and we call them a coalition. And a grand coalition is all the players in the environment. And you basically have some sort of imputation, some sort of total payout or reward for the coalition. So there's the entire kind of group of players that are potentially working together, and that's what the coalition is kind of implying, has some amount of reward that they're going to share potentially in some fashion. And individual rationality as a player should earn, not earn at least what they would by having done the work alone. So they should, working together should result from an individual rationality perspective being at least as good as if they had done it themselves. Making collective decisions. So this is where you basically have kind of a concept of, you've got a group of potentially equally of agents involved, and so there's several ways that we can approach this approach. One is called a contract net protocol. This has been around forever. The basic idea is that one of the agents says, hey, I've got a problem. They reach out and make an announcement to the group, hey, I've got a problem, you want to help me with this? Each individual agent bids on that problem, and the person or the agent with the problem then awards that work to one of the agents at some cost. Been around for quite a while, kind of follows this, modeled after most likely the whole bid approval, going with the lowest bidder and government work and whatnot. There's other approaches and elements to consider. You may have this concept of auctioning off of scarce resources. You may bargain amongst the agents to where they trade this for that to get something. You may even have elections and the agents individually vote on some outcome. And you assume that they're going to probably follow the outcomes of these various things of bargaining and elections and resources because they're trying to avoid conflict. That also may lead to this concept of a reputation. So an agent could end up having a reputation if they act in a certain way. If they say they're going to do something in exchange for something else, you give them the something else and they don't do what they said they would, then that's going to affect them negatively, may tie into it. If you're really interested in this more, here's a couple links that you should go check out. It's an interesting topic. Again, you could go take a course on it if you're so inclined. So moving on to chapter 19, learning from examples. And we're going to first talk about the forms of learning. So what is learning? It's basically getting something, information out of your environment that helps you do something better. It modifies the agent's decision making to improve performance is the idea. The various types of learning. You have supervised. So there's a labeled data set that you know the answer. So you may have some values or say some emails, and you know which ones are spam and you know which ones are not. You may have some other information where you don't know the answer, and that's unsupervised learning. And so in that situation, a lot of times all you can do is potentially look at patterns in the data based upon attributes and cluster them together. So you may figure out a group of people's musical preferences based upon the things they listen to, and maybe that I listen to the same things you listen to so that we like the same things and you can cluster us together, that sort of concept. Reinforcement learning, you don't really know the answer, so it's not a labeled data set, but you have some way of measuring the outcome, and then the thing that's doing the learning can adjust based upon what maximizes the outcome. So maybe they play a game of chess and they know if they win or they lose, and that's all they need to know to learn with enough trials of doing different things, and there's a certain amount of randomness whenever you're dealing with reinforcement learning to eventually win. This is the architecture of a learning agent. We talked about this some time back. These are the various elements associated with learning. So you talk about what type of performance elements being used, what's the functional component to be learned, the functional component represented, so how is it, and what kind of feedback is available. Moving on to supervised learning in more detail, this uses a labeled data set. So you have this concept of a training data set, and this is data set that has been coded with outcomes. So you know some values and you know what the answer is. So if it's an image data set, you know that it's a picture of a cat, you know that it's a picture of a dog. And your ground truth is the true answer. So it is essentially the label. And generally you'll use that term in the context of the test set. You generally, when you're doing any kind of learning, especially supervised learning, you're going to do some data exploration. You're going to learn about the data before you do anything. You're going to determine a best fit function, something that fits the data, but not too well. You want to be able to generalize, and that basically means you want to be able to predict on data that you've not seen before. Because if you're not careful, you'll either underfit where you don't find the pattern, or you'll overfit, which means you basically map on the data that you've seen too much so that if you see something you haven't seen before, you don't recognize it. And those are kind of the ideas, and you want to find that right degree of enough but no more. And there's various ways that you can start determining that, and it's something that is a pretty precise sort of thing. The Occam's razor is very true. For those of you who aren't familiar with it, it's basically the simplest solution is often the best. There are some exceptions to that, but the basic idea is if you have a series of points, which you can see there, some overly complex function that produces the one line that is all over the place. Turn on the laser pointer and point at it. So this line out here, probably not the best choice. This blue one, that looks pretty good. It kind of is fitting them all. Red, probably too simple, so that's probably underfitting. So this isn't exactly an example of overfitting. Overfitting would be it follows it exactly even to the point that it can't see something that is not quite right. So moving on to learning decision trees. First of all, what's a decision tree? A series of kind of nodes. A node has arcs going to other nodes that represent decisions that can be made. There's probably going to be other things we add to that over time, but that's the basic idea. Is it's a way of almost like a simplistic flow chart with the only real things are states and branches. So you can basically express any function with a decision tree. So it is a pretty powerful thing, and you'll see a fair amount of them. The hypothesis space, the number of Boolean functions. So how many distinct decision trees with n Boolean attributes, 2 to the n, right? Or 2 to the 2 to the n, depending upon which one we're looking at. So how do you learn a decision tree? So the idea is here, given some training data, how do you come up with a decision tree? The algorithm here, that's pseudocode, might work. I haven't tried it. But anyway, moving on to kind of a more relevant topic is model selection. And so how do you figure out which one to use and rate them? So going over some concepts and terms, you have a key term here called error rate, and that's the ratio of how often you get it right. So it's the ratio of the predicted outcomes to not right. Obviously, you want a low error rate. A high error rate would mean higher than 50% is you're not as good as chance, which isn't good. So whenever we talked before about labeled data, this is in supervised training. There are 3 kind of basic sets of training labeled data that you'll use. or label data that you'll use. One of those is training. You use that to train with, so that's basically to try to figure it out. You'll do a validation, which is used to help you pick the right model. So you do some training, then you use some validation to figure out if it's the right approach. It's something you haven't seen before, but it's not the test set, which is the last thing, which is how you're actually going to use to measure your performance. So just how good you're doing to determine an error rate. And you always hold that back. The system should never see it before you use it. Otherwise, you're going to be biasing your results, and you'll do better on your test set than you would on something you haven't seen before. And that's what you're trying to do, is come up with an estimate for how good will this thing perform in a situation with data it's never seen before. Hyperparameters are things that you can use to essentially turn the knobs. It's parameters that are used for a model class, not for a certain model, but for a class of models. And it's used to optimize the overall process. A loss function is something that you're trying to minimize. You're trying to minimize the loss. It's kind of almost like the inverse of utility. You maximize utility, you minimize loss, and that means that you're going to be doing descents rather than hill climbing. So you're going to be doing some form of gradient descent or some form of descent, not trying to go up. You're going to be trying to go down. Population-based training, that's where you basically train models in parallel. You figure out which one of them does the best, and you keep trying, fiddling with the various attributes and such until you get something that does pretty well. Commercial offering, Azure AutoML, does some of this stuff in that sort of thing, but not that thing. What Azure ML does, similar sort of process. Azure ML is a managed service that lets you do machine learning in the cloud. AutoML basically lets you try your data with hundreds to thousands of different models to figure out which one is going to do well programmatically. You basically set up the equivalent of the utility function, or the loss function is the thing that you're trying to maximize or minimize. So some measure, usually something like area under the curve, and run it, and it'll tell you here's the one you should use based upon the data you have. So something pretty cool. I'll try to talk about it in the future if we have time. Moving on to the theory of learning, concepts and terms. It relates to the field of computational learning theory. This basically is applying mathematical mathematics to learning systems. You deal with a probably approximate correct concept. And what that basically means is that with enough testing, if something isn't proven to be terribly wrong, it's probably not wrong. If you want to learn more about it, the link's on the screen. Definitely worth digging into. Again, pretty advanced topics. Moving on to linear regression and classification. So basic concepts here. Linear regression is about, like a univariate linear regression is a single variable, and you're drawing a line. That's literally what you're doing. So you're trying to find a line that fits points the best. When you talk about gradient descent, you're talking about it's the opposite of the utility function. You're not going to be climbing hills. You're going to be trying to find the lowest point so that you can minimize loss. A linear classifier is something that splits things into, in this case, two classes. You have a line or a surface, and a surface is when you start getting into higher dimensions, that you use to separate two classes of things. The challenge you have is that not everything easily separates, especially in a two-dimensional sort of way. And we do some tricks to get around that. When we deal with linear classifiers, you have the inputs or feature values. Each feature has a weight, and the sum is the activation. We talk about logistic regression. What this does is allow us to get from a binary decision about if something is in or out of the space and move into something that's more of a sigmoid sort of function that allows us to have a range to where it becomes 0 or not. And so you'll end up with something that's not a hard line like you see in A here, but more something that moves. And that helps you out whenever you have things that are closer to the thresholds. So how do you get a probabilistic decision? Through the use of a sigmoid. So multi-class logistic regression, similar sort of concept, but obviously you've got more than one or two classes that you're classifying. So you can start thinking of yourself of going into higher order space potentially. So how do you convert the scores into probabilities? Here's the example of how this math all works out. Non-parametric models, all a non-parametric means is basically that it's not a function that can be expressed or can't be expressed with a function with a set of parameters. Sometimes it's going to be something done through an additive sort of approach. Sometimes it may not really work that well. So in order to do this, it requires instances based or memory based learning to address this. Generally speaking, you're going to be talking about nearest neighbor models. So you'll hear something like K nearest neighbor. That's where that comes from. It's based upon the distance in some way of calculating distance, be it Euclidean or something else, but the distance between points or readings. And the idea is to get those things to where they're the closest together. So you find essentially this what would ideally be a centroid of a cluster, and then you find the things that are closest to it. A kernel is a function with inputs of distances that essentially maps it to a higher dimensional space. And what this lets you do is basically it's considered a trick of taking something that you can project it into higher dimensions, and then you'll be able to do a linear classification to where it's not something that's going to be linear in the current space. So it's kind of an interesting topic. Support vector machines is a class of models for supervised learning. They were really popular, but the deep neural networks kind of took their spot as the golden child. What they basically do, and they have some characteristics that are pretty cool, they create a maximum margin separator, the largest possible distance between between the example points, and enables for good generalization, which means that it can handle things it hasn't seen before very well. And it does what I just mentioned of the kernel trick of basically mapping into higher dimensions so that you can separate things that is difficult to separate with a linear function in the way that they're formatted initially. Using a hyperplane in a higher dimensional space. They are non-parametric. Support vector machines are non-parametric, so that means they only need examples that are close to the separating plane. You don't have to have all the points that they might ever see, just those that are close to the boundary. If you want to learn more, the link on the screen is a great resource, a good place to start. And in general, that towardsdatascience.com, pretty good set of blogs and posts. Ensemble learning basically is just about combining together multiple models, and we call them base models, into an ensemble model. And the basic idea is you take them, you put them together, and in some way, they're voting, averaging, or something else, you combine them together to get a good result. And there's several ways to create these ensemble models. One is bagging, where you basically are doing k distinct training sets out of with n examples, and so you're basically grabbing various randomly sets of the data and using them separately. You've got random forest, which is a similar sort of concept, except you're choosing what attributes that you want to consider, not necessarily the training. So it helps you figure out which of the variables or the attributes of a given set of items is probably the highest value, the highest information. Stacking is when you combine together multiple base models of different classes trained on the same data. So you might take things that are essentially different kind of companies or different types of classes or of backgrounds or approaches, and use them together, having trained them previously on the same data. And boosting is a way of taking a weak learner, which is one that's not that much better than kind of random, into a strong one, and you do so by using weights. And the most common one you'll hear about that is gradient boosting, and that's about using an iterative boosting using a functional gradient descent algorithm. So when you hear that term, that's what it's about. So when we move on to this last topic is around regret. And the idea there is that whenever you're making a decision, you may not make the best decision, and there's going to be some way of calculating you're making that decision so that you might have should have done something else. Moving on to developing a machine learning sort of environment. The process is kind of what's outlined on the screen. You start by formulating a problem. you go out and you get yourself some data and you start taking a look at it and you start cleaning it and extracting the stuff you care about. Then you move on to model selection. You want to keep an eye out for false positives. You'll want to use something like a confusion matrix to keep track of how often you're getting it wrong. And you may want to use something like this receiver operating characteristic curve as a means of kind of rating how good you're doing. You also then want to move over to this kind of domain of trust, interpretability, and explainability. The idea here is you're kind of getting closer to making this into a real thing. You want to get it underneath version control. You want to do lots of testing and reviewing. Can you explain the model and why you get the results you do to someone in a believable way? And can you explain why the results are what they are? And can I interpret what those results mean in a way that makes sense? Does it align with my, as a business owner's perspective on how something should work, or is it totally opposite of what you would expect? Once you do all this stuff, you actually will deploy the model out for use. And typically speaking, you're going to push it out into some sort of a web service. And again, that's where Azure ML is an interesting thing combined with AutoML. It makes it really easy to take a model that once it's figured out this is the best one to use and push it out for consumption. You want to make sure it keeps running. That's where you're going to be monitoring it, and you're going to make sure you're going to be maintaining it. The only thing you don't maintain is the things that aren't being used. And so with that, we reach the end of this discussion. If you have any questions, reach out to me. That's what I'm here for. As always, stay safe, and I'll talk with you next week.